You're on.
Thank you, Ron.
Hey.
Thank you. I'm here all week. Yeah, so just so I can kind of calibrate the talk, how many people here have never heard of lambda calculus? Seriously? Okay. We'll start with the beginnings. The lambda calculus is a formal system that was invented in the 1930s as a model of computation by a fellow named Alonzo Church. And it has, for our purposes here, only two constructs. It has lambda abstractions, which look like that, and applications, which in the original notation look like that, and one reduction rule that basically says to apply a lambda expression to an argument, you evaluate the expression part of the lambda expression with the variable substituted for the value that's being passed in as an argument. The original lambda calculus actually has two more rules called alpha reduction and eta reduction, but they don't matter for our purposes. That is it. That is all that the lambda calculus is.
Looks like Polish notation.
Hmm?
It looks like Polish notation.
It's yeah, I suppose. It's just a formal system. So it's a system, you manipulate it, you do symbol manipulation on it according to the rules, and interesting things happen. Today we're going to be using slightly different syntax because this is a Lisp group, so instead of the original syntax with the dot, we're going to write lambda expressions as a list of three symbols, the first one of which is the letter lambda, and applications as a list of two symbols. And I'm also going to introduce a little bit of syntactic sugar because the lambda calculus itself has only functions of one argument. But in order to make things a little less annoying notationally, I'm going to introduce the syntactic sugar for functions of multiple arguments, and those are just going to get curried. So this is a function of multiple arguments is just a macro that expands out into nested functions of single arguments. And by extension, a function of no arguments just returns its value. You don't have to actually call it. There is no distinction between a function of no arguments and the value of the expression that's in the body of the lambda expression. And that is it. That's all we have to work with. It has no data types other than functions. It's got no const cells. It's got no numbers. It's got no booleans. It's got nothing. And yet it is Turing complete. And that is what I'm going to demonstrate to you today by using the lambda calculus to write a function that computes the factorial of 10. Not only computes the factorial of 10, but does it by compiling the lambda calculus code that does it into native machine code, and then runs that machine code and will actually produce a result in non-geologic time. Which the first time I saw that happen, it blew my mind. And maybe I'm hoping it'll blow yours the way it blew mine. So the question is, how is this possible? Because when you learn Lisp, the basics of Lisp, you start out with these primitives that include cons and car and coulter and cond. And we are told, if your education is typical, that you need to start out with these given as primitives. And it turns out that you don't need any of those. You can actually build all of these things out of lambda. And the punchline is that this is a factorial function. That tiny little bit of code that consists of nothing but lambdas actually computes factorials. And the first time I saw it, I didn't believe it. Actually, let me leave this on. And so to demonstrate that to you, I have here a completely clean common Lisp environment. And I'm going to introduce into that common Lisp environment a single macro for lambda. And I'm not going to go to the details of what this lambda macro does. The main point is that there's not a lot of code. And what it does is it makes this Greek letter lambda act like a lambda calculus lambda rather than a common Lisp lambda, which is to say it's a currying Lisp 1 lambda, and that's all that it is. And because it's a macro that actually compiles lambda calculus lambda into common Lisp lambda, we can actually run it directly. And we can say something like funcall lambda x plus xx and call that on the number 3. Oops. the text is very tiny on my screen here. And it just compiles to Common Lisp and runs it. So here is the Factorial demo. I'll just run it for you. There it is. That's how quick it computes the factorial of 10. Just to prove to you that it is a factorial of 10, here's the usual Common Lisp factorial of 10. So you get the same number a little bit faster. But just to take a look at a little bit of what's going on here, this is the actual code that I showed in the previous slide. That's the factorial function. And the rest of the code that's wrapped around it is sort of a driver that calls that function with the number 10, which actually is this thing, because the way that this function represents numbers is with something called church numerals, which I'll get to in a minute. But this is the church numeral 0. Just take my word for it for now. So it's calling this function here, which is a function of f and s. F is the factorial function being passed in here. S is a function that adds 1 to a church numeral. So what it's doing is it's taking 0, adding 1 to it 3 times, computing the factorial of that. So it's computing the factorial of 3, which is 6, adding 4 to that, which is 10, and then computing the factorial of that. And then in order to convert that into a format that we can read, it calls that on the Common Lisp functions, the Common Lisp function that adds 1 to a number and the Common Lisp number 0. I'll get to details of how all that works in a second. So in order to make this a little bit easier to follow, I have some debugging macros that lets us give names to these things and kind of expand them out, because if we didn't do that, in fact, I'm just going to get my whole environment up and running here. If we didn't do that, all we would see were these spaghetti codes of lambdas, and things would be very hard to follow. So this just lets us build functions of the lambda calculus and give them names so that we can look at them and make things a little bit more readable. Okay, so how do we start building up the ability to actually compute from nothing but functions and no primitives? Well, we start out by building an if statement. And to build an if statement, we start out with by building booleans. So what is a boolean? Well, a boolean has to be a function. It has to be a function because that's all there is. Everything in the lambda calculus is a function. And so the way we build an if statement is by essentially building a function true that takes 2 conditions, a then and an else condition, and returns the then condition. And false is going to be a function that takes a then and an else condition and returns the else condition. And if then is going to take the condition, true or false, and a then and an else, and just call the condition true or false on then and else. And the net result of that will be that if the condition is true, then we'll get the then value back, and if the condition is false, then we get the else value back. So here's an example of it working. If true 1, 2 returns 1. We can build a not function the same way by basically inverting true and false. So if not true, 1, 2 returns true. Is everybody following this? So now we've built an if statement. But this if statement has a problem because it's not really an if statement, it's an if function. And because it's a function and because we're compiling to Common Lisp and Common Lisp has eager evaluation, it's going to evaluate both the then and the else clause before returning the value. So if we have side effects in here, lambda calculus doesn't have side effects, I'm just doing this to illustrate that these 2 things are being called before the value is returned. And they're both being called regardless of which value is being returned. And this is going to cause us a problem because later on we're going to try to build recursive functions, and the recursive functions are going to have base cases where we want the evaluation to stop. And if we tried to do that using this if statement, it would just go into an infinite recursion and we'd get stack overflows. So there's actually a paper that I wrote about this, and I put a pointer to it on the newsgroup. In the paper, I actually wrote that in order to fix this, we need to cheat a little bit and use Common Lisp's if statement. And so I introduced this little hack that I call double underscore if that expands out into a common Lisp if. Turns out that's actually not necessary. You can build a real non-eager if directly in the Lambda calculus, and the way you do it is that you wrap the then and the else here and here in lambdas in order to delay their evaluation. And then you wrap a parentheses around the whole thing in order to evaluate the result that comes back. And so now you're evaluating only the condition that comes back. So just in order to be able to keep these two things separate, the original eager if has one underscore, and this new non-eager if, which does have to be a macro in Common Lisp, but it's going to expand only into lambdas. It's going to expand into single underscore if. So we're not really cheating here. This now has two underscores. And now if we do double underscore if true, we only get the one that we selected being evaluated.
Question.
Yep.
I thought that your macro makes a no argument lambda equivalent to the body.
Yes.
Which would make it eager. Is that not the case?
That's right. So the reason that this lambda is out here is because this little piece in here that's actually doing the work is actually not legal Common Lisp. So in Common Lisp, unlike Scheme, you can't actually have a form in the car position of a form unless that form in the car position is an actual Common Lisp lambda, which is it starts with the symbol CL lambda. One of the things that the Greek letter lambda macro does is it sticks in fun calls for you everywhere that fun calls are needed, so that you can actually write this double open, so that you can actually have a form in the car position and it will get evaluated properly. And so this lambda out here is just so that that transformation gets applied to this the call to the Lambda calculus compiler. Does that make sense?
Yeah. but then where is the x coming from? I know you don't need an x. At some point you have to provide the value for the result of the con, right?
Yes. So where's the x coming from? So remember that these are all curried functions, so that you don't actually have to pass an argument to them. Where's it coming? That is a good. Yeah. So if you call a function of one argument without an argument, it just returns itself. So maybe this double paren is not even necessary. I'll have to think about that. But I'm a little bit leery about changing it because it might break the demo. And so there's one other thing that I'm going to. Let me just show you one other thing. If I macro expand this, which normally I would do with a function key that's on my numeric keypad, which I don't have here. So let's see if this is going to work. I have to do it the old-fashioned way. So that you can see that fun call is getting stuck in there. If I do a macro expand all, then this is, that's the Common Lisp code that this is all being, that this ultimately gets all expanded out to. And I also have a function called LCP, which stands for Lambda calculus pretty print, that expands all this out in terms of lambdas. So if I, for example, lambda calculus pretty print my not function, then it all comes out looking like the lambda calculus code. All right, so now we have a conditional that works. So the next thing we need to build is concells. And we build concells in kind of the same way that we built conditionals. We're going to have a function that takes in a car and a cdr, which I'm going to call the left-hand side and the right-hand side in order to distinguish lambda calculus concells from Common Lisp concells. So a pair is going to be a function that takes a left and a right and returns a function that takes a selector, which is going to be a function that picks one of these out, and that these selectors are going to be the equivalent of car and coulter, or in our case, left-hand side and right-hand side, and calls the selector on the two components, and the selector is going to pick out the right one. It's exactly the same as how conditionals work, actually. In fact, the structure of the code is exactly the same. So the left-hand side is left-hand side, or car, is a function that takes a pair and calls the pair with a selector that takes the two components and returns the left-hand side. The right-hand side does exactly the same thing, except it returns the right-hand side. So if we take the left-hand side of a pair whose elements are the common Lisp symbols left and right, then we get left, and likewise the right-hand side of a pair is whatever's on the right. So now we have a const cell. Now we need something to be the equivalent of nil, or the empty list. And that actually turns out to be a little bit tricky. I'm not going to go into the details of how nil and null work. You can go reverse engineer it for yourself afterward, but I don't want this talk to take forever. But the bottom line is that nil is going to be a function that's going to be the only function that, when fed to the function null, returns true. And all other functions, when fed to the function null, have the property that they're going to return false. So null of nil is true, and null of anything that's not nil is going to be false. All right, so now we have const cells, and we have conditionals, so now we essentially have Lisp, right? So now we can build anything we can build in Lisp. So, so these straight, well, except for one thing, and I'll get to that one thing in just a second. How are we going to represent numbers? Well, the most straightforward way of representing numbers, since we have lists, is we're going to represent the number n as a list of length n, right? So, and we're going to call these numbers pair numbers. So all the functions that have to do with numbers represented this way are going to start with pn for pair number. So pair number 0 is just nil, and the function that tests if a pair number is 0 is just null. And to add 1 to a pair number, we just make a new pair that has an extra element tacked on at the beginning. Everybody following this? And if we want to subtract 1 from a pair number, then we just take the coulter of it, take the right-hand side of it, lop an element off. Now this is a utility function that makes a pair number out of a common Lisp integer. So if I do pn10, that's going to be a function. That's going to be the lambda calculus representation of a list of 10 elements. And if I print that pair number, then it'll walk down that list and count how many elements it had to walk before it got to nil. And so this is how we're going to test this code. So now we can define a function that adds pair numbers in the usual way. Now we're essentially writing Lisp in Lambda calculus. So double underscore if the pair number n2 is 0, then the result of adding n2 to n1 is just n1. Otherwise, it's the recursive call where we add the successor of the first argument, or 1 plus the first argument, to 1 minus the second argument. And this actually does work. So if we print the result of adding the pair number 5 and the pair number 6 and print that as a Lisp integer, we get 11. But we've cheated. And the reason that we've cheated is because in here we've made a recursive call to pn plus. And the reason that's cheating is because the Lambda calculus doesn't have names for anything. Right? All these names that we've given these things that lets us refer to them, that's common Lisp scaffolding that we've added for debugging purposes, but it's not part of the Lambda calculus. So how do we make a recursive call in the Lambda calculus? And this is the answer to that is one of the most brilliant things that's ever been come up with by mankind. It's a Lambda calculus function called the Y combinator. Has anyone here, besides you, not heard of the Y combinator? Okay. Does anybody here not understand how the Y combinator works? Okay, I'll go through it briefly. I don't really want to get too deeply into the Y combinator. There are really good tutorials on the web. that walk you through it step by step. And it actually will ultimately turn out that we don't need it at all, which is kind of interesting. But this is the straightforward, intuitive way of building this stuff, so I will show you how it's done using the Y Combinator. It turns out there are different ways of building a Y Combinator. Here are 3 different variations on it. The Y Combinator, what it does is it takes a function that's almost recursive and turns it into a recursive function. And what do I mean by almost recursive? What I mean by that is we're going to take a function that takes one argument. That one argument is going to be a function that we are going to assume is the recursive function that we want. We haven't built this function yet. We're going to assume that it's just been magically provided to us. And using that magically provided recursive function, we are now going to write the actual body of the function that does the computation that we want, given that we've assumed that we've been magically handed the recursive function that we want. So this fact star is almost the factorial function. So and this is now, I'm using common Lisp here. So if the number is 0, then you return 1. Otherwise, you multiply n by the factorial. And we're now assuming that this function f here is the factorial function. And because we've bound it with this lambda, we are allowed to call it. So we're calling the factorial of 1 minus n here. So what the Y Combinator does, and let me see if nope, I didn't make a slide for the Y Combinator. Sorry about that. Thought I did. So I'll have to just wing it. What the Y Combinator does is it basically solves the mathematical equation that you get when you write down the constraint that you want the Y Combinator of this fact star to be equal to the factorial function, which is this function called on the factorial function. So you write, and I think I might be getting some of the details wrong here. It's basically you're solving this equation, y of f, no, f of y of f equals y of f. Yeah, I think that's it. Because if you take f and you pass it the factorial function, you want the result to be the factorial function. Or maybe I've got this backwards. Look it up on the web. The point is, it's solving this mathematical equation, and the solution to this mathematical equation, for when you solve for y, turns out to be that. So that's the Y Combinator. So we're just going to, so y is just this lambda calculus expression that takes a function and does some magic stuff to it to turn it into a recursive function, to pass it back into itself in the right way that it can call itself recursively. And so now if we fun call y of fact star on the number 10, we get the factorial of 10. Pretty cool, right? Mm-hmm. Yep.
Can you write the Y Combinator with the macros?
With the macros. This is the Y Combinator here.
Like with ifs and stuff? Like with the ifs and like doubles?
It doesn't have any ifs. It's just a lambda calculus expression.
Right, but you can like compile to like...
Oh, I can macro expand this out into common Lisp if you want to see what that looks like. Macro expand all...
You missed a beat.
I'll do it this way. Yeah, the type on my screen here is much smaller than it is on the screen. There. That's what the Y Combinator ends up looking like in common Lisp. So
That's kind of dumb comment.
it's kind of hairy.
Usually,
Is I'm applying the lambda calculus Y Combinator to a common Lisp function fact star that operates on common Lisp data types. Now I'm going to unroll that bit of cheating and do everything in the lambda calculus. So now, because remember how we got to this point in the discussion, we were trying to add two numbers. And we got everything that we needed, except we had to make this recursive call, and that was still cheating. And so we introduced the Y combinator so that we could do recursive calls without cheating. So now we're going to go back and build our pair num math in pure lambda calculus with no cheating. And here's what that looks like. So here's the addition. Pair num plus is the Y combinator applied to a function that accepts a function as input, which it's going to assume is pair num plus. And then it's going to return from that a function that takes two numbers and do the usual recursive number addition on it. If it's 0, if n2 is 0, then the result is n1. Otherwise, you make this recursive call to f, which is now legal, now not cheating, to n1 plus 1 and n2 minus 1. And in exactly the same way, we can define pair num multiplication by making recursive calls to pair num addition. And we can even do pair num exponentiation, and we don't really need it for the factorial, but I mean, now it's easy, so you might as well. And it's kind of cool, because now we can do, for example, print pair num exponentiation of pair num 3 and pair num 4. I wonder if this is actually going to work. Yeah, so there is 3 raised to the 4th power done in the pure lambda calculus, and you can actually print out what that function looks like using this lambda calculus pretty print. Oops. That's interesting. The exponentiate. So what this does is it expands all the lambdas out, and this one turns out to be so hairy that it overflows the stack. Let me see if I can print out addition. Never. Well, that's interesting. Something's ended up being broken here. This really should work, and I'm not sure why it isn't. Well, these don't actually matter so much. But later on, it'll matter. If the later on ones are still broken, I will go back and try to figure out what's going on here. This is really weird. I've run through this a zillion times, and this has not happened before. Anyway, so here is the pair num factorial function.
Maybe it doesn't like the font size.
Maybe it doesn't like what?
It doesn't like the font size.
No, that's not it. Because it's overflowing. Somehow it's got an infinite loop in it. I think it. Oh, you know what I think it is? I think I screwed up my if macro somehow. Let me try rebooting this. Yeah, okay. Something I typed in must have screwed something up. So there's the lambda calculus exponentiation function. You will notice that it consists of absolutely nothing but lambdas. Yeah, it really is kind of amazing. But it's kind of hairy, right? There's a lot more code here. Oh, let me show you the factorial, which is what we're really interested in here. There's the factorial function, the pair num factorial, which we can now test. All right, so here is the pair num factorial of 6. And let's see how far we can get. 7, not bad. 8, still kind of working. Let's see how far we can push our luck here. 9 is starting to get kind of slow. And our goal here today is to compute the factorial of 10, right? So let's see if we can do it. Take my word for it, it's going to be a while. I've never actually let that one run to completion yet. I have no idea how long. how long it would take. And also, the code here is a lot more complicated than that end result that I showed you, right? So at this point, it kind of feels like an academic curiosity, but not really useful for anything practical, right? So, yeah.
You may have mentioned which kind of equality is used throughout this EQL? EQ, what kind of equality?
So you'll notice we actually haven't defined EQL. We've only defined null. So the only test we actually have is a test for the empty list, because the only kind of data type that we have are pair numbers, and so the only thing we really care about is whether it's 0 or not. So there is no EQL yet. And actually defining EQL is tricky because everything's a function, and the halting problem means that you can't actually tell whether two functions that are not EQ are EQL or equal or do the same thing or have the same lambda calculus expansion. You can't tell that within the lambda calculus itself. You have to go meta and look at the expression that describes the function, not the function itself, right? Talk about that
So you can't
more offline.
theoretically.
Well, you can do everything because it's Turing complete, but it's tricky. And
But you said it would be like solving the halting problem. It would be like solving the halting problem.
well, no, because the way that you would have to do it is you would have to embed the lambda calculus within itself in the same way that you embed S expressions inside of Lisp. Because we've essentially built Lisp here, right? And so if we built Lisp, we can do anything that we want to do in Lisp, except that we don't have symbols yet, and we don't have numbers. So we have to somehow build those into our system so that we can manipulate them as symbols and numbers, and then we can build equal tests and all those other fun things. But we don't have any of those things yet. All we have right now are pair numbers, and all we can do with those is test them. All we can do with those is represent positive integers, and the only test that we built so far is testing for 0. So we could actually build an equality test if we wanted to. Later on, I'll actually have some equality tests. Turns out it's easier to build not equal or greater than is easier to build than equal. So the way you write equals is you write greater than first. You build less than out of that, and then you write equals as neither greater than nor less than. We're getting into the weeds here. We have now computed a factorial with the lambda calculus, but it's slow and not really practical. And we want to see how far we can push this towards something that is really usable. So the first thing that we're going to do is we're going to change our numerical representation from pair nums to something called church numerals. And this one I do have a slide on. So the reason one of the reasons the pair nums are inefficient is because they cons. Every time that we add one to a pair num, we're making up a new con cell. Worse than that, we're doing that by consing up a new closure, because all of our con cells are functions and they're being compiled into Common Lisp. So we are allocating memory like mad. So we can make that all a lot more efficient by using a different representation for numbers that was also invented. This was actually the original representation of numbers in the lambda calculus that was invented by Church, hence the name church numerals. And a church numeral is a function of 2 arguments that is normally, I really should not have called this n, I should call this x. Let me just fix that, because otherwise it's going to be confusing. Oh, yeah, that is just a mistake. So the number n is going to be defined as a function that takes a function and some argument. I actually didn't need to put this here because of currying, and then it's going to apply that function to that argument n times. So, the church numeral 0 is a function that takes a function and an argument and applies that function to the argument 0 times, which is to say it just returns the argument. And then to add 1 to a church numeral, that is a function that takes a church numeral as its argument and returns a new church numeral, which is to say a function of a function and some argument, and applies this function to its argument one more time than it was originally applied. Now, there's a little bit of a subtlety here, which, again, in the interest of time, I'm not going to go into the reason that this is written as nfx instead of just f. Just take my word for it, there was a reason. There's a reason for it which I can't describe succinctly right now. If you're really interested, catch me offline or go read the paper or something. There are then standard definitions of addition and multiplication that were worked out by Church back in the day. The reason that we don't need the Y combinator here is because Church numerals themselves are kind of like for loops. So if you take a Church numeral and apply it to an argument, a function and some argument, you're iterating that function n times. And so you can use the Church numerals themselves to drive loops. You just call them on an argument on some function, and you're iterating that function n times. So, for example, if you want to multiply two Church numerals, you just call two Church numerals m and n. You just call the number m, which is to say iterate m times, the function that adds n are atomic and opaque, and can't take them apart the way we can take pairs apart. So what we have to do is we have to start counting up again until we get to a point where applying the function one more time gives you the same result as the number that you're trying to subtract 1 from, and then you go back and return the previous number. And that big mess is implemented like so. And now we can subtract by iterating, subtract n from m by iterating subtract 1 n times on m. So now we have, there's another, there are lots of different variations on these themes. The one that's really cool is that to exponentiate, it turns out that exponentiating, taking b to the eth power, is just calling e on b. If you call one Church numeral on another Church numeral, what that works out to mean is exponentiation. And the bottom line is now we can define a Church numeral factorial. This one uses the Y combinator, but it's now, and we have these.
You're using the double underscore if just for like efficiency's sake?
No, remember the double underscore if is the non-eager evaluating version of if.
Yeah.
It's the one that lets you have it inside a recursive function without running into an infinite loop.
And you did define that within Church numerals. I remember seeing it like as common Lisp.
Right. So this double underscore if is a common Lisp macro that expands out into a lambda calculus expression that wraps then and else in lambdas.
It is all like compliant lambda.
It is, and to convince you of that, let me show you what it expands out to. So here's the Church numeral factorial.
Got it.
Again, nothing but lambdas. Notice it's quite a bit smaller than the pair numeral factorial. So it's looking promising to be a little bit more efficient. So let's try it out. Cn fact. I've got Cn and Pcn are just helper functions that convert integers into Church numerals and Church numerals back into integers. So Pcn is print Church numeral. Cn is just Church numeral. So there's the Church numeral factorial of 6, 7, 8, 9. Looking good. Think we can get 10? Yes. So you can get to this point without really having to think too hard. I mean, there are some little tricks in here that you have to kind of study and think about for 5 or 10 minutes to really wrap your brain around them. But using nothing but that, you can get to the point where you can compute the factorial of 10 and compile that code into machine code and run it in about a second. Let's see how long we've got here. Just a little over a second. That's not bad. But here's another cool thing.
And only a gigabyte of content.
Yeah, it's still conting a lot. It's still conting a lot. But here's something that I actually don't know what the result of this is going to be because I never tried this one. The actual computation of the factorial itself is much faster. What's really taking all the time here is printing the result. And the reason that is because remember, the actual result here is a church numeral. And a church numeral is a function that iterates n times. So converting that number to an integer is going to be order n. So we have to do at least, however much this is 3.6 million iterations of adding 1 in order to get to the end, in order to convert the result into something that we're used to reading.
So does this mean that actually C in fact is lazy? If you do C in fact of 100?
So it depends on what you mean. So C in fact itself is not lazy because it's working on church numerals. So C in fact, when I compute C in fact, this result that I get is actually the church numeral representation of the factorial of 10.
So I'm saying if you did 100 there, would it finish it with that?
That's right.
So it's not simplifying it somewhere along the way.
What this is doing is it's producing a function that takes a function as input and iterates that function by the factorial of, in this case, 100 times. You can actually look at this. Oops. There's the machine code. It's page and a half of x86 assembler. Let's see. How are we doing for time?
Because 157.
Yeah, about 45 minutes so far.
Yeah. All right. Maybe I'll just stop here because where it goes from here is to talk about various kinds of optimizations that you can do to get the 1 second that it takes to actually expand out the factorial of 10. We can get that down to about a quarter of a second. So another factor of 4 speed improvement that you can get by applying various kinds of optimizations, which are kind of cool because these are optimizations that are generally applicable to functional code. What we're really doing here is inventing functional programming from the ground up. And so you can start adding continuation passing style and closure hoisting and all kinds of cool stuff. And that's how you end up with that one-liner that I showed in the opening slide. And it's kind of interesting, but it's time-consuming to go through it all. So I think I'll just leave it at that. If you're really interested,
Performance optimizations on it? You're doing actual performance optimizations?
That's right. That's right. So you're taking this is really the code that we're running here, and this code is optimizable to the point where you can shrink it down to that one line that I showed in the opening slide, and the result of that is a factor for runtime improvement, and also I think it also stops conting too. Let me just jump down to the bottom here where I've got my where did my these these are all these lambda expressions here are steps along the line of doing these optimizations so that you can go through step by step and understand them all. But let me just find, yeah, here it is. BF. This is the BF fact is the Felgen. The one-liner was invented by a fella named Bertram Felgenhauer. And so that's this BF fact function. And if I time BF fact, let me just go ahead and print church numeral BF fact, numeral 10. Yeah, so there's a quarter of a second. And with this one, this is normally the punchline for this talk is now you can dial it up to 11. And it actually still works. But so the cool thing here, oh no, it's still allocating a lot. So never mind that. But there's actually another optimization that we can do because we don't have to use church numerals. We can actually build binary arithmetic out of lambda calculus. And we do that in sort of the same way that we built pair nums, except we give ourselves a 1 and a 0 bit to work with. And now we've taken all of our operations and optimized them from order n to order log n. And that's a fairly straightforward elementary exercise to go through, so I'm not going to go through the details, but I just want to show you this is sort of the preliminary version of that written in common Lisp, just to give you an idea of how much code it is. If you translate it, when you translate it into the lambda calculus, it ends up looking like this. And so now we have a binary number factorial that we can binary number en fact of binary number of 10. Now that's really fast, and because it's binary, because it's order log n, now we can actually compute the factorial of 100 in pure lambda calculus. It's now, let me widen this out so it's not quite as annoying to look at. Yeah, still can't quite get it all on one page. So this is the binary number arithmetic version of the factorial. Again, pure lambda calculus, nothing but lambdas. And of course not written by hand. It's, built out of the development system that we've built up kind of on the fly. But it actually works. You can compute the freaking factorial of 100 with this. And I just think that's really cool. So the upshot here is the lambda calculus is more than just an academic curiosity. You can actually do real things